So good morning. Good morning, everyone. My name is Lorenzo Castelli. I'm associate professor in operation research at the University of Italy, or University of Trieste in Italy. And I'm really glad to have the opportunity to moderate this trajectory prediction session at the 10th SESAR Innovation Days. We have two presentations, so we have two speakers. The first one is Jose Manuel Cordero. He's going to talk about traffic characteristics for a dynamic and adaptive trajectory prediction data-driven approach. Jose Manuel is a principal researcher in ATM since many years, and his fields of expertise include operational performance monitoring and management, advanced computing data analysis, and data-driven causal and predictive models. He has been involved in several projects, and also I would like to mention the fact that he received two important awards: the Jane's ATC Environment Award in last year in 2019, and the Maverick Sustainability Award in this year, 2020. He's in Creta. And also since August 2019, so since last year, is a member of the Eurocontrol Performance Review Commission, so the PRC of Eurocontrol that everybody knows very well. So I'm really pleased now to give the floor to Jose Manuel for his presentation. And as you know, you can have the Q&A through the Zoom panel. So if there is any questions, then I will collect the questions, and then I'll make the question on your behalf later on. So Jose Manuel, please go ahead. Thank you.
Thank you, Lorenzo. Good morning, everyone. Thank you very much for the kind presentations, the kind words, and it's a real pleasure to be here today. I missed the opportunity to meet everyone face to face as was initially planned, but I mean, I hope those times will come very soon again. So I will start by sharing my presentation, which I hope you can see. So yes, as Lorenzo just said, we are going to talk a bit on the traffic characterization for a dynamic, adaptive trajectory prediction with a data-driven approach. These three pillars, dynamic, adaptive, and data-driven, are the cornerstones of the research that we carried out in a project called Diapason that has been the guiding research activity under which we have conducted this activity or these results. So actually Diapason is part of the Engage KTN, which is actually, if I may share this, is a very interesting. I mean, MOVE has been a nice formula, short project, just 1 year, but something that was already quite mature. And with this Catalyst Fund, we have had the chance to further elaborate and bring in closer to industrialization some features that were already promising. So in particular, this Diapason project, which stands for Data-Driven Approach for Dynamic and Adaptive Trajectory Prediction, was included in the thematic challenge number 2, which is again working on this data-driven TP, trajectory prediction. And the pillars were these three, as I said. Data-driven, first, as we are just relying on data, on actually in this case in operational data coming from ENER, as I will elaborate in a minute. It was intended to be dynamic because we were willing to adapt this framework, this trajectory prediction framework that we were elaborating to different time frames, to different planning horizons, let's say from strategic to a few hours before operation, and actually very close to before operation. And we're due to the nature and the evolving features of the data that we were using, we were designing it in a way that was adaptive. So evolving according to the new patterns, the new features of the data that we are using, because it's trying to reflect the behaviors of the different actors in the system, actually reflects the way that airlines introduce their flight plans. And this can change, of course. So we were designing this framework in a way that could illustrate or at least incorporate this in practice. So we were willing also to give some flavor. As I said, the project was really limited in time, so it was just 1 year, but application was essential. As I said, this Catalyst Fund were something already close enough to operation. So we were willing to validate that in a use case, which in this case was DCB, demand capacity balancing. And here it's important to mention that we are not that much interested in individual trajectories, but we are interested in the global trajectories. I mean, a set of multiple trajectories in order to support this DCB use case with occupancy counts and so on. So the individual trajectories are of course within scope, but not that focused on them. Okay. So the Diapason consortium was formed by CRIDA. Of course, we were taking the lead, and we were doing providing some operational background and some data management, in particular from the data coming from INER, the Spanish ANSP that we are linked to. From our colleagues from Deep Blue, they were leading the activities in scenario definition and management, and also in validation activities that were very important, as I described, and also our Cenabite colleagues, which were mostly in charge of the technical part of analyzing data, implementing the models and machine learning, etc. Just to mention that Cenabite is a spin-off of University of Genova. And I would like to mention as well that the excellent cooperation that we have during this work is very difficult in such a reduced time frame to get a team to work together, and I mean, is something I'd like to mention as well. So the operational context in where this focus, so there are some assumptions, is that we are on a TBO, on a trajectory-based operational context, considering 4D trajectories. Okay, even though we are going to be focused in the planning stage, as I described, so very focused more on the current shape of flight plans. We are always thinking of extension to 4D trajectories and application to that kind of operational context, where, as you're very familiar with, the controllers are intended to progressively assume a less acting role to work in a more monitoring role, let's say, so that they monitor that the operations are working according to planning and to act only in the case of need. It's also acknowledged globally that predictability is a key enabler, a key driver for enhanced performance in the ATM system. In particular, you know that increased predictability will reduce the existing buffers, and for sure it's going to bring additional capacity, much needed in the nominal conditions. Of course, these reductions of uncertainty will help to enhance safety as well, to bring benefits in terms of cost efficiency and as well in environmental impact. So it's a win-win for everyone trying to reduce these buffers. And it's also important, and on a different stage, to relate this to the potential loss of flexibility, which is not exactly like that. But anyhow, it's quite accepted, quite well accepted generally, that predictability is essential for boosting performance in ATM. So with this was here and showing a picture of the, actually this, I brought this slide to the last SESAR Innovation Days. We were having a workshop in Engage. So this was normal conditions 1 year ago, more or less, when we were all in Athens. And the picture on the left is showing a forecast on the network operation plan in the NOP, beginning of December. And the picture on the right is showing the same situation just 3-4 hours later. So still in planning phase. Okay, so it was showing what would happen in the afternoon, but early in the morning and later in the morning. So you can see how the situation evolved. And thing is that while this evolution is something that you could clearly expect, we find that when you look at the NOP regularly, you find that there are some patterns here. It's not always going for worse. Actually, you can see that the situation in some cases, in some places, actually improve, as in Turkey. So these kind of effects are something that we can observe patterns, and thereby we can exploit them to the benefits for our planning, in particular for practical and strategic planning. We think that this, and we have research in this direction, that the evolution of this, without taking any action, just the information we count on planning phase, can be exploited actually to refine the forecast that we have. In particular, in this case, applies to TCB, but can be applied to other use cases. So I'm going to start by describing the data that we are using in this project, which is slightly different from the usual data set that we tend to manage. We are using operational quality data from a Spanish ATC platform from ENER. The platform is called SACTA. It's also moving to ITEC. And we are getting every flight plan update in every flight phase. I mean, from pre-tactical to the landing phase, to the landing moment. So actually what we are getting here is in DDR, you normally know that the initial flight plan is the last flight plan before off block. And here we have plenty of flight plans updates for the same flight before that. This gives a huge potential, because actually what we are considering here are the set of flight plans that are entering the actual ATC system in planning phase. So it's not what airlines know, but what the ANSP knows. Okay, so this is has a strong potential, because we have also observed that the different behavior of the different airlines is bringing some value to this. Here we are seeing two different examples from two different airlines. The bottom axis is showing the time before departure. And here we can show the airline on the left that is delivering most of the flight plans like 17 hours before off block time from their respective flights. It might happen that many of these flight plans are not actually very accurate. Okay, it's something to be analyzed later on. But here you see that there are not too many updates of those flight plans. So you can see that the information here comes early enough to be used in ATFCM processes, and also is quite reliable. There are not too many updates. On the contrary, on the right, you have a different situation where just a small set of flights is coming at 17 hours before operation, but the biggest amount of them comes between 4 and 6 hours before operation. So that means that for planning purposes, this might be a bit too late to make good use of it. So if we are considering of planning the next shift, actually it's a bit too late. And actually, if you are planning to set, let's say, a cutoff time, let's say for planning. So imagine that you are trying to build a demand forecast based on flight plans, and that you are willing to determine if a flight is going to fly or not, respective to a reference that can be the previous week, for instance, and that you want to know if a flight is going to fly this week as well. So if you are considering just to look at this moment in time, let's say 2 hours before operation, as an example, you would be missing, if you are only looking to flight plan existing in the system at that given time, you would be missing, in the case of this airline, you would be on the safe side. So it's good, the picture is good, but there is no one-size-fits-all solution here. So you would be missing a lot of flight plans in the case of this second airline, as in many others. Okay, so it's important to paint this picture as well. So if I may show this as well here, just because this might be a bit confused for some. Here we are getting the first instance of a flight plan for a given flight. Okay, this whole timeline is referring to the same flight. We get a first information of a flight plan. So this is the first indication for the ATC system that a flight is actually going to fly. This is issued by the airline in the ATC platform. Okay, and then this is setting an estimated off-block time. Okay, might happen that a second iteration of a flight plan is changing some information, in particular in waypoints, etc., due to upcoming weather information, any cost function, any issue happening in the network, etc., and as well might update the estimated off-block time. A set of flight plans can be issued as well, and normally there's like 3, 4, let's say, before off-block update of the flight plan, some of them very minor. And this is the flight plan that is considered the initial one for DDR. Okay, but we have a lot of information beforehand. actually tactically, live data, you know. So this one contains the last, or the final EOBT in the case that the flight is not regulated, of course. And then it turns into a EOBT. And then we have a tactical phase where the changes in the flight plans correspond to the air traffic controller, mostly services. So we are, in this research, we are looking to just the blue part, not the green part. So it's trajectory prediction, but focus on the planning stage. Okay, so there are few questions arising here that has potential to be exploited. So is flight plan 0 reliable enough to be used? Well, not in all cases, in some cases, but when is reliable enough? What is the difference between the first flight plan and the last flight plan before off block in path and time? Is something to look at as well. Is flight plan 0 early enough? In some cases, as we saw before, in many cases, for a given airline, it's coming 4 hours before off block. Is that good enough, or we need to forecast that, or we can wait for it actually to happen? So we don't need to forecast everything. And most important, and comprising everything, how can we use this information to enhance demand forecasting? So this has been the context of this research that we are doing here. And entering a bit more into the technical detail, we have put in place a few metrics. Okay, the first one is called the similarity one. You have the formula here, which is mostly looking at how many waypoints are kept in the different updates of the flight plan with respect to the final one. Okay, so how similar the flight plan is to the others. So this has already allowed us to look at well, a set of flight plans. So the data set in this case was 3 months, different months in the year. So we were trying to avoid the seasonal effects by considering winter and summer months here. And you can see here that most of 70% of the flight plans are showing no actual difference in the flight plan. So they are around 0, the similarity. So they are very similar. And only 10% of them is actually showing a change of more than 50% of waypoints. That means that most changes are not happening, but still a number of them, like 30%, are happening in terms of waypoints. So meaning that most of the changes are happening with respect to the temporal dimension. Okay. Here, so we introduce another variable, which is called the delta t, which is the difference between the EOBT of a given flight plan record and issue and the timestamp of the first flight plan, meaning the anticipation. What before we were showing how early, with respect to the off-block time, the the flight plans were coming, so giving us the potential to be exploited in planning purposes. As well, this is showing that the delta t has a similar behavior to the in terms of path, even if you look at the different colors here, they are showing different intervals. So meaning that the anticipation is less than 2 hours, so actually very, very close to operation, between 2 and 6 hours, 6 and 9, etc. So you see here that they have a very similar behavior, despite how early it was issued. And according to our research, which is true, is mostly based to let's say, airport-related weather phenomena, this weather doesn't seem to have a big impact in this flight plans update. This is a bit unexpected, I may say, and it's something that should be deeper analyzed, because maybe this just looking at the weather-related regulations or airport data is not enough. We need to look to some data ensemble in a different for en route, because here we are focusing mostly on en route. So it's something that that possibly can be deeper analyzed. We also went deeper. We went deeper in the analysis per airline, where you can see we were grouping by European legacy carriers, low-cost carriers, and non-European. And you can see there are no big difference in terms of grouping, but on the contrary, there are big difference in terms of individual airlines. So some airlines were very close to 0 dissimilarity, so meaning that any flight plans is already very similar to the final flight plans, very few changes in planning stage, while there are some others that are showing higher levels, average levels of dissimilarity. Here we are using as a parameter to represent. The average is not good, because as you have seen before, the distribution is quite asymmetric. So here we are using the percentile 80 as representative value. But as a trend, you can see that low-cost carriers are bringing lower levels of dissimilarity than legacy carriers, was something that you can possibly expect. When we look to airlines, we look to reliability. So we are looking here to the average time at will any issue flight plan becomes identical to the last flight plan before EOBT. Here you can see the picture as well. You can see that well, there are again significant differences between the times, and for instance, Iberia Airlines or Turkish Airlines are reliable. This means completely similar. Maybe we could set another threshold, just 90% similar or whatever. So just 3 hours before off block, while others are around 8 hours before off block. So with all these parameters, we built a predictive model here that we were trying to look at different time horizons, as we said at the beginning, by being dynamic. We are looking to 8 hours, 4 hours, 2 hours, and 1 hour before off block. So for each time horizon, we were following not a too complex predictive model. We think that this can be exploited in much more complex ways, possibly. But here we implemented the logic here that is, well, the existing instance of the flight plan is compared to the historical flight plans, removing from the sample any flight plan not coinciding. If the current flight plan is not the first one for that given flight, and the previous sequence is not matching any historical sequences, that sequence is already discarded. And then we are, for the remaining flights, we are taking the last off-block plan, the last off-block time plan trajectory. We are considering that as the most frequent in that set. So we are taking that as the forecast for that given flight in planning phase again. So the accuracy we are achieving with this model, that again is not the most complex in the world, that can be fine, but we're here just for trying to apply to a DCB use case, is that we are getting better results with comparing to the default accuracy. Default accuracy meaning taking the existing flight plan at that moment on time as the final one. Here we are using a different logic to consider which is going to be the final one. And we are getting better results in more, let's say, strategic, without being strategic purely, time horizons, like 8 hours and 4 hours. We are getting better results than in 2 hours and 1 hour. This is, of course, something that you can expect, because when you get closer to operation, the flight plans are more and more similar to the final instance. This is quite intuitive as well. And well, we are seeing here for airline, this is again showing different time horizons, 1, 2, and 4 hours, and we are seeing that the patterns are similar for different airlines. For sure, the closer to the operation, the better that we are able to predict, the highest accuracy that we get. But the level of accuracy is pretty good, and actually we are getting over 80% for the great majority of airlines, and still we think that this has the potential to be further explored. So what we are showing here is that this initial unpredictability, when we are looking at the first instance of the flight plan that maybe you could consider to discard, is systematic enough in most cases to become predictable and thereby exploitable. So it's possible to estimate the probability of change for every flight individually and apply them to any use case, in particular demand forecast, or we could even give a confidence value for the forecast mix. So we have confidence values per individual flight. So here, for instance, we have an example for Lufthansa. We have a sample set of individual flights where the average probability of change is very different from some flights that never change. And actually here we are discarding flights with very few appearances in the sample. So here all are repetitive flights. Some flights practically never change from the first flight plan to the end, while others are changing more than 75% of the information in it. Okay, so within the same airlines, the difference is there are still some noticeable differences. So and very quickly, because I think I'm running out of time, we apply this to a DCB use case with a set of assumptions, because in the flight plans information that we were getting, there were no vertical profile information, so no actually 4D trajectories. So we tested a set of dates, and we were comparing with information in Nest. And we were using two Spanish en route sectors, one upper space and one lower space, and we were considering to 4 hours, 8 hours and 4 hours before operation, just to give a flavor of the results. And yeah, well, here we are seeing in light blue the actual flights, and the others are the actual count of existing flights with the prediction. The gray and yellow for 4 hours, and dark blue and green for the 8 hours. So here we can see that it's not actually matching the final results for a set of reasons. We thought that the assumptions were maybe too I don't know how too strong maybe, and we need to refine those assumptions. But still, we need to refine this for the application, but I think gives an idea of the potential that this has in planning phase. In particular, to do this, and it's the last part of the presentation, we were conducting some interviews with some operational staff from Eurocontrol, ENAF, and INER, as you can see there, and to ask them how such a predictive tool could fit their actual operation and of planning at a strategic level. Well, this is the workflow they agreed on. So try to have demand predictions compared to demand coming from flight plan information and compared to capacity threshold. So we actually delivered a kind of mock-up where you can see the difference, both in an aggregated way in terms of occupancy counts, but also in terms of individual trajectories. Okay, so this was just a final flavor to try to look for some potential application, and actually the feedback from this operational staff is something that we expect to be able to take into account in further research. So just to conclude, I would like to highlight that the project obtained a framework, not an actual single method, but a framework that is considered that has the potential to explore the flight plan information in planning phase in a data-driven, dynamic, and adaptive way. We think that we have demonstrated as well the potential of exploitation of this information that is not generally available, but maybe we should try to make it available, not just to look at the final flight plans before of block. We have also identified that there is no one-size-fits-all model that can fit every airline. So there are different behaviors, and actually even different behaviors within the same airline. So we need to focus maybe even at an individual flight level. And we have also demonstrated that the model brings significant benefits in the prediction accuracy for the most variable flights. For sure, if you have a flight whose flight plans is not changing over time, you are going to observe little to no benefit. But if you have a very valuable flight plans, you're going to observe a significant benefit. And the application to the DCB use case that was performed at the very last stage of the projects needs to be refined in order to observe and to really deeply be able to quantify the potential for exploitation. So that's all. I hope I make it on time, Lorenzo. Sorry.
Okay, so thank you very much, Jose Manuel. Yes, we have a few questions in the Q&A, so thank you very much. And I will just take a couple of them because we are slightly running out of time. So, but I'm sure that if people would like to contact you by email and so on, then you can provide some more details. I guess. You know, I think that's something you can do. So we have two questions from Sebastian Wangnik, Eurocontrol. So one is a kind of comment which I think is really interesting. So we can now start talking about 5D trajectory management. So it's 4D trajectory evolving over time. So it's a kind of fifth dimension. I think is an interesting comment here. And he also asked if you had a look into predicting the flights that have not yet been filled at all at the given prediction horizon.
Not in this case, but definitely that's something we would like to look at. Yeah, indeed, it's something actually that's the key question, because it's easy to determine when a flight that flown in your previous reference, let's say last week or last day, is going to fly, but it's very difficult also to identify when it's not going to fly until when you wait. So it's something, and in particular in this direction, that we would like to focus, but it wasn't analyzed in this case.
All right. Then we have a question from Xavier Olive. who's going to ask, what kind of contributing factors did you find in data for delta to EOBT?
Actually, that's a question that it depends on the different airlines. Sometimes it's just fleet management. You know, is the airlines are reacting to changes in their in the network, and something that reactionary delay is reflected in the EOBT. But we have identified that in some cases, some airlines are releasing the first iterations of the flight plans as placeholders. So the information there is not reliable at all for any purpose that noticing that the flight is actually going to fly. But in those cases, the EOBT, there is no factor, mostly that reflecting actual information. So first you release a placeholder and then you release the actual information. So the factors in the changes for EOBT, depending on the different airlines, but mostly they are related to actual operations, fleet management, and weather phenomena for sure.
All right, I'm going to take two more. So thank you. From Gennady Adrienko, did you try to investigate spatial-temporal patterns that could explain differences between often changing versus stable Lufthansa flights?
No, good morning, Gennady. No, actually, we didn't research for that, and I think that I'd like to ask you to help us on that. So, it would be a nice piece of analysis. I guess no spatio-temporal analysis was done on individual flights.
Okay, and there is from Okwari, from DLR, Okwari Osheichas. I'm sorry if I mispronounced the name. If the duration of flights, the distance flow correlate with the schedule predictability. Is there any difference between short shuttle flight and long interval? No.
In terms of waypoints, for sure, the more waypoints, the more likelihood you have to that a change in one of them is impacting a percentage, but not in terms of time. We observe, if you look at, in particular, to the non-EU flights that are normally a longer radius flights, we observe that they give similar values to the internal EU flights. So it's not something that we can set a direct and clear correlation.
Okay, so thank you. I think I have to stop here now because we are the other presenters. But Jose Manuel, if you go in the Q&A, you see there are still a few questions that I have not the time to answer. So maybe you can try to answer.
To do live, yeah. I try to answer very quickly as well, so maybe I can extend in some answers.
Yeah, exactly. So and now we have the time, so we leave now. Okay, so thank you. It was really interesting, and I also have many questions, but I think I don't have the time. So maybe I will contact you later on. So thank you very much. It was a very interesting presentation. So we now give the floor to Matthias Poppe, that he's going to present us clustering climb profiles for vertical trajectory analysis. Matthias received a diploma in electrical engineering from the Technical University of Braunschweig in Germany. And then after his PhD, he joined DFS. So it has been working since he joined DFS in 1995. So he worked in research and development departments, and he's very expert in data link, MODES, and future ATM management concept. So, and he's currently involved in SESAR Wave 2 flight-centric ATC. So he made quite a lot of work in this in this domain, and now he's trying also to use the field of machine learning, feed-forward vectors, and apply to this field. So thank you very much, Matthias, for your presentation, and now the floor is yours.
Okay, thank you. Good morning. Thank you, Lorenzo, for the kind introduction. So my presentation is about clustering climb profiles for vertical trajectory analysis. And now we are looking to the tactical domain in my presentation. So what is the motivation? You all know we need higher levels of automation, and one of the key enablers, that is for sure, that is an accurate 4D trajectory prediction. So all the ATM systems, controller decision support tools like conflict detection and so on, they all rely on accurate 4D. So what we have today is a quite high uncertainty in the vertical profile, because the vertical profile depends really on many factors, and factors we often do not know, like the atmospheric conditions, the aircraft weight, the takeoff weight in particular, the cost index the airline is using. We have operational restrictions in the departure path, and we have human interventions from the pilot, as well as, of course, the clearances of the controllers, which sometimes stop or level off climbing flights. So recent research, we have a focus on the improvement of parameters, for example, the aircraft mass, or also looking at the cost index and so on, to feed parametric models that are available. I think the most known of these models is the BARDA model. So what we are looking at, and what we didn't find too much literature about, is what is the situation looking at all the aircraft types and taking real world operational data. So we don't want to focus on a typical, or one or two or three typical aircraft types, but looking at the overall situation. And so what is the magnitude of the problem for the departing flights? And then another question related to this is, can we predict clusters of aircraft with similar climb performance, and can we make use of it for forecasting trajectories in the vertical domain? So that are the questions we are looking at. And here at the right-hand side, you see an example of a flight, and you see the deviation of this city pair, which is quite significant. So what do we use as a benchmark? You see here on the right-hand side density distribution over the time from takeoff to flight level 250. So we have chosen a bit arbitrarily flight level 250 as a benchmark, because that is, let's say, the overall lower airspace for climbing flights. And it is well below the crossover altitude, where we have some effects when the aircraft switches from the CAS regime to the Mach regime. So we have chosen this flight level for this reason. You see that what we also did, we filtered flights with level of segments. So when the flight obviously got a controller level of clearance, let's say stop climb at flight level, I don't know, 200, then we didn't look at this flight, because that would, let's say, disturb the overall picture, and it's not an unrestricted climb. So we tried to filter and to look at only at the unrestricted climbs, at least where there's obviously no controller level of clearance. So the distribution here, what you can see, it's an empirical distribution from the departures from Frankfurt and Munich airport, and we looked in total at about 45,000 departures in the year 2019. So what we see here is a mean of about 700 seconds, and the standard deviation of 108 seconds. What you can also see is that the distribution has something like a Gaussian shape, and it ranges really from 400 seconds from takeoff to flight level 250 up to more than 1,000 seconds for this climb part. So that shows, I think, very well what is really the problem, because if some flights only need 400 seconds, others need more than 1,000 seconds, of course, that is a challenge we have here to forecast for the individual flight, what will be the climb profile, what will be the time needed to flight level 250. So what is the approach? We used an unsupervised learning to discover some structure in the data, to structure the data. And we have seen, we have decided to base the clustering on the Euclidean distance function, which can be nicely used in this case. I will show this in the next slide. What we also did is quite a radical step in reducing the very high dimensional trajectory data to flight level over time, and we sampled every 10 flight levels. So we sampled at flight level 10, 20, 30, and so forth to eliminate a little bit the noise in the data. So what we need or what we derived then is a vector of a constant length. And that is very important because if we want to use a Euclidean distance, we need a constant length vector. If we would work with vectors with different lengths, we have a problem then in applying the proper distance measure. So we decided here to use as a clustering algorithm the well-known k-means because we see some advantage here. One of the advantages is that all input data will be assigned to a cluster. That is different if you use, for example, density-based clustering algorithms, where you may have a lot of noisy data which are not assigned to a cluster. And that is something we think is better if you have all flights assigned to a cluster. And on the same time, the k-means provides us a cluster representative, and that we can use for further analysis. So what the algorithm does, the k-means, it partitions the observations into a predefined number of clusters. So that is something we have to choose the number of clusters beforehand, but that's all. And another quite nice thing is that the clusters are disjunct. That means they are not overlapping. And the algorithm simply minimizes the within cluster variation, in our case here based on the Euclidean distance. So coming to the data preparation. So we used, as I said in the beginning, 45 climbing flights from Frankfurt to Munich, and we collected the data from the OpenSky database. We took the MODES data, the enhanced surveillance data, and we added the aircraft type as it was known. So if you look at the typical climb profile at the left-hand side, the diagram, you see here the flight level on the y-axis and the times on the x-axis, so as we get the data. The problem is now that the times to climb to flight level 250, they vary significantly, which means we would have a different vector length if we take this as it is. So we decided then to use a kind of inverse climb function with piecewise constant flight level segments. And that has a big advantage that for every climb profile, we have a vector of a constant length. In our case, with 23 segments, they were extracted. So that you can see on the right-hand side, we have now time on the y-axis and the flight level on the x-axis. And so we have the flight level divided in constant average 10 flight level in constant segments. And then in the vector, for example, for T0, we took the time needed to climb to flight level 30. So the T0 will be different for every flight, as well as the other entries in our vector, like T1, T2, and so forth, up to T22, which is the time then needed to flight level 250. So that was a trick here we applied, and that works pretty well, as I will show you now in the results. So we started with 6 clusters, and on the left-hand side, you see all the samples from all flights. And we see here the clusters and the time needed to climb to flight level 250. So you see here the distribution between 400 and the 1100 seconds. And you also see, because I've colored here the cluster members, that the clusters, they are kind of overlapping, but only the cluster members are unique to a cluster, but of course the times, they are kind of overlapping. But we can pretty well distinguish the clusters. If you look at the right-hand side, the cluster representatives, excuse me, for the 6 clusters, then you can see that we can quite well see distinguished cluster representatives which do not overlap. So that means based on this Euclidean distance between the cluster representatives, we can assign a flight to a certain cluster, and then we can kind of have an idea about the climb performance of this flight. I continue with this example of 6 clusters. If you look into the different clusters, you can look at the cluster representative, and then you can have the mean of this cluster, and you can have a standard deviation. If you look at all the if you look at all the cluster members, all the flights in this cluster, and you just compute the distance to the cluster representative, and you got the variation, the variance that you see in this cluster. The results, you see that the standard deviation is about 30 seconds for the cluster 0, 1, 2, 3, and 4. And if you look at the cluster 4 and 5, that means the slow climbers, they have a higher standard deviation, which is about 45 or 55 seconds here in our case. And then in the right column, you also see the number of cluster members. So we have fewer members for the fast climbers, and even less members for the slowest climbers with a mean of 900 seconds. On the right hand side, I have shown you the aircraft types within each cluster. And if you look, for example, at cluster 0, so the fast climbers, you see, the A319, A320, 20 Nero, Boeing 738, and so on. So that's not surprising, I guess. And if you look on the other hand at the cluster number 5, the slow climbers, also not surprising is we see a Boeing 748, Airbus 388, 321, AAA, Airbus 330, and so forth. So there seems to be some logic. It makes some sense. But what was surprising to me, we also see an aircraft type like the A321 that appears in both clusters. So obviously, for this aircraft, it has a very different performance. Yeah, based on factors we often do not know. Maybe it's the aircraft takeoff mass. Maybe it's a cost index. I don't know. Maybe it's atmospheric conditions also. So that's a bit surprising. And if you see a A321, so it from this analysis, it will be very difficult to say beforehand, hey, the performance will look so or so. Now, what we did in the next step, we increased the number of clusters, in this case to 10 clusters. And what now happens here, that is something which was a bit surprising, because suddenly we have a cluster member, and you see it here with the arrows, with the red arrows. This cluster representative that is crossing the other cluster representatives. So in the beginning, it has a quite low performance, this particular cluster members, but then around flight level 100 or so, the performance changes, and compared to the other cluster members, is not suddenly, but the cluster performance becomes better. So the assumption is that this is caused by the acceleration phase from 250 knots, it's around flight level 100, 1010, to the final constant, to the final CAS, and maybe that depends really on the airline policy, cost index, mass, whatsoever. But the conclusion is that this makes a prediction extremely difficult in this climb phase, because if you observe only in the beginning, the first, let's say 5, 6, 7, 8 samples, we see, or we could think, oh, it's quite a slow climber, but then suddenly the behavior changes, and this cluster member shows a different behavior compared to all the other cluster members. Coming back now to the 6 cluster case, we were curious about the prediction capability if we have 6 clusters. So what we did is then we looked how much could we assign the correct cluster with only partial knowledge of the feature vector? So let's assume only the T0 to T10 are known, which means in our case, prediction takes place at flight level 130. So, and then we can, with the cluster representatives, find the K that satisfies this little equation with the argmin. So we find the K, which has the closest Euclidean distance to the closest cluster representative. So in this case, we took 10,000 unknown queries. So we only sampled 35,000 for the K-means. And we had 10,000 unknown queries and we applied it. And then we have seen that the accuracy, so the correct forecast, we could forecast the correct cluster in about 70% of the cases. So what you see here is a confusion matrix where we have the predicted cluster versus a true cluster. So the predicted cluster, that is a column, the true cluster, that is a row. And then you can see the diagonal, that means the correctly forecasted clusters, the correctly predicted clusters, which is here quite strong diagonal. So that is a 70% of the correct forecast. But of course, you also see always some clutter, some wrongly predicted clusters. But on the other hand, we have a lot of zeros in this matrix, which is good for our forecast, of course. So if we go a bit further, here again, the example with 6 cluster and analyzing the prediction capability. Of course, we cannot be better than the variance that we have within one cluster. And so for 6 clusters, if you look at the root mean squared error, it's about 37 seconds if the correct cluster was predicted. But on the other hand, if you could not predict the correct cluster in 30% of the cases, we have a pretty large error of about 87 seconds. And if you look of the overall accuracy here, then it's about 57 seconds. So that means forecasting only based on the Euclidean distance gives a result which in many cases may not be good enough depending on the application. And we think that additional features are required to achieve a better cluster prediction. As I've said, we reduced dramatically here the trajectory dimension only to 2, but with this flight level over time, we can have a 70% accuracy for 6 clusters, which is at least a good starting point, I'd say. So coming to the conclusions of this analysis, clustering the, let's say, real-world profiles is successful. We can do it with 6 clusters, 10 clusters, even more clusters, if you use the inverse climb profile and if we eliminate the noise in the data. We have a limited prediction capability, I'd say, based on the Euclidean distance between the cluster representatives. And as I've mentioned, the accuracy is then given by the in-cluster variation. Maybe you could also use some k-nearest neighbor or whatsoever to improve even the in-cluster variation, but that is something we have not yet looked at. Increasing the number of the clusters leads to a problem. We have overlapping cluster representatives. And the big question is, can we predict this behavior based on additional features, which we not looked into this in this study? And that is also an open question. Maybe controller clearances were still available in the data that have restricted the climb, and that are the cause of the observed behavior. We don't know it because we don't know the controller clearances for a particular flight. What we propose is to use this first approach based on the k-means and complement it, for example, with a naive Bayes to take into account other features. So we we could use the aircraft type that we can find in the cluster. We could use something like indicated airspeed. We can estimate the aircraft mass. There are some papers available with pretty good approaches for estimating aircraft mass. And maybe if we know the cost index airline data, of course, I'm quite sure that will improve the forecast. So the profile clustering in that case can be used as a priori knowledge that simplifies, or is a good starting point for the classification task for predicting the vertical climb profiles. And that concludes my presentation. Thank you very much for your attention.
Thank you, Matthias, very much for your presentation. There is quite a few questions that popped up during your presentation. We should stop the session now, but as we start a few minutes later, I'm sure that we are allowed to move on a few minutes more. So I would like first to give the first question you might try to answer is from Soner Demirel, that it was the very first one. So if you can tell us if there is any similarities between level of times of flights in terms of duration.
Again, what do you mean level of times?
I don't know exactly. So it's
in duration. So what we have seen, I've done an analysis. So how many flights were restricted by controller clearances? And that's in our case for the Frankfurt and Munich departures about 35%. So what that means, 65% of the flights, so 2/3 of the flights are more or less not restricted by level of clearances, but I can't tell you, let's say, the duration of a level of clearance. But that I think that can range from seconds to maybe minutes even.
All right, thank you. So there is more than one person that is more or less asking the same question, which is related to the number of clusters. So we have Federica Leonetto. So she says, how would you choose the optimal number of cluster? What would you expect to be the impact on the result of the performance? And this is related also to a question from Adita. How do you decide the cluster numbers for the key means?
Yeah.
And also how you address the outlier noise uncertainty issue in your data using k-means. And also is Gerald Gürtner has asked, how have you considered using an algorithm without a predefined number of clusters? So otherwise, what criteria would you choose for the number of clusters? So there is more than one person is more or less addressing the question about the number of clustering, the number of clusters, sorry.
Of course. So the number of clusters, that is a free parameter. And of course, it's quite critical how to choose. The first thing is the more clusters we have, the higher the K is, the smaller is in general the in-cluster variance if the cluster if the clustering is successful. The less clusters we have, the higher the variance. So that is a general observation, let's say. But what I have done is I have calculated the sum of squares, so the distance of the sum of squares to the cluster center for all the cluster representatives versus the number of clusters. So, and if you look at this diagram, that's also in the paper, that you can see a quite sharp decline between 4 to 6 clusters. And then if you increase further the number of clusters, then this sum of square is not so much decreasing. It's further decreasing, so that's a good thing. But the sharpest decrease is between 4 to 6 to 8 clusters. So that's the reason why I have chosen 6 clusters as a good number. But if you have 10 clusters, 16 clusters, and so on, I also tried this. Then you can see this problem with the overlapping cluster representatives. The other thing I would like to mention that is correct with the outliers. That is something k-means is quite sensitive to outliers, and I tried to apply this filter to eliminate the outliers, but of course I can't be 100% confident that there are no outliers in the data. If you look at 45,000 flights, I mean you have to rely on your filtering.
Okay, thank you. Thank you very much. Then there is just a very last question, and then you may also, as Jose Manuel, try to answer in the Q&A because there are many unanswered questions. So if you have some time, that would be great, I think. So at which time this is from Sebastian Van Geek, Eurocontrol. At which time early in the climb can you determine to which cluster a flight might belong?
Yeah, well, that is I have tried with the first 10 data points. So in my example was flight level 130, and then I'm at the ratio of about 70, maybe a little bit more than 70%. So, but if you want to be if you want to be more, if you want to have more than 90%, then of course you have to wait longer until you can be very sure, based on this Euclidean distance k-means, to which cluster the flight belongs. So that's really a function of the number of clusters and the time or the flight level when you do your prediction.
Okay. Okay, so thank you. I think you have to stop here, but these are a few questions that I would really invite you to answer, because I also people is more or less supporting this kind of question. So I would say thank you very much. Okay, thank you very much. Now it seems that there is a teaser video for the other. Okay, bye-bye.
Bye-bye, thank you.
Thank you.
Welcome to FARO. FARO stands for Safety and Resilience Guidelines for Aviation. FARO is a project funded by the SESAR joint undertaking under the European Union's Horizon 2020 Research and Innovation Programme. FARO is composed by 7 members: CRIDA, Eurocontrol, ENAIRE, Universidad Politécnica de Madrid, Lund University, University of Belgrade, and Cenabite. We aim at 4 different objectives: defining a safety and resilience framework, define a predictive capacity for safety, conduct resilience analysis, and conduct validation, and design safety and resilience guidelines. Please visit us in our safety and resilience webinars on the 9th and the 10th of December. Thank you very much.